Hey guys, David here and welcome to another Dark Art Guitars video. Today I want to take you through my process for cutting one of my guitars on the CNC. I'm going to start at the very beginning, cut step by step, and especially focus on the cam, like what kind of tool paths that I'm using, what tools am I using, how fast am I going, and all of this I am doing, of course, on my brand new CNC. So this should also give you a bit more of an idea of what this machine is capable of. I'm going to start off with body blank. I'm going to cut the arm bevel for it so that I can do the bent drop top that I like to do on it. I'm going to show you how I do that. I'm going to glue that up, machine the rest of the body. I'm going to machine the neck on both sides, as well as doing the fretboard with all of the inlay. And with all of that, the start of the show here on my new CNC is this Spinergy X22 Spindle. I want to give a big thanks to Spinergy for working with me to get this into my hands. Without them, this would not have been possible. And especially when we get looking into the fretboard and all of the very intricate inlay where I'm using teeny tiny little tools like 0.3 millimeters, stuff like that. Having the 30,000 RPM on this spindle is a godsend. And of course, having a tool changer, I don't have to tell you just how amazing that is. And that saves me a ton of time as well on all of these different parts. Now this is probably going to be a very long video, I don't know yet, but you can look at the time down below. So there's going to be timestamps below. I'm going to go through component by component. I'm going to show you my cam toolpaths on the computer and I kind of overlay the real cutting strategy. But in all the cases, I'm using the dust shoe and you can't really see much of the cutting action. That's just if I'm creating a bunch of chips, then, well, I don't want to breathe those in, so I'm using the dust extraction, but that kind of ruins the camera work a bit. There are some like things with smaller tools where I don't need the dust shoe, so there you can see a bit more, but otherwise you'll have to be content with the computer simulations. So without further ado, let's jump over to the computer and get into it. So this right here is the guitar we're building. It is quite similar to the one I built here on the channel fairly recently, except this time it's going to be a 6-string version and we have a poplar burl top instead of a buckeye burl top. Other than that, we also still have a black limba body, and here this time the neck will be with some walnut, padauk, and some nice flint maple. Now, all of that doesn't really matter for the cam strategies here, but I thought I'd just kind of share with you what we're building. What does matter a bit more is that we're using a tremolo bridge. This one here is from Nova Guitar Parts, and I'm also using their block headpiece. Usually I like to use the single headpieces, but the customer for this guitar requested this different headpiece, so that's what we're using here. And that's why also the headstock here looks a bit different than it does usually on my guitars. Now, if you want to learn how to design guitars like this inside of Fusion 360, I have a separate video where I go over a bunch of tips and tricks, and I also have a Fusion 3D guitar model available for sale on my website that can get you started if you want to design your own headless guitars inside of Fusion. There is also some cam in there, but it is not like fully fleshed out. And that's mainly because the cam is so dependent on what kind of machine you have that it is very hard for me to provide like a general template. Let's go over into the manufacturing space here. And as I've already alluded to, cam is very dependent on your machine. I'm going to be using here my newly built Dark Art CNC, and it is quite capable. It's fairly rigid, so I can take some quite heavy cuts. And of course, the Spinergy X22 Spindle that I'm using is absolutely amazing. It has up to 30,000 RPM spindle speed, 2.2 kilowatts of power, but power usually isn't really the issue on one of those desktop machines. But it also has a tool changer. So there are a couple of things here that I would do differently. If I, for example, didn't have a tool changer, I would try to consolidate the tools a bit more and not use as many different ones. And once we get to like more of the inlay stuff, then, well, of course, your feeds and speeds are going to be slower if you don't have 30,000 RPM, but only 24,000. I'm going to try to kind of give some references to what you might be able to expect on a different machine, as I expect most people are probably on a slightly less rigid machine than this one, but it's generally more intended as kind of a starting point and to give you some ideas about the strategies and not as something that you can copy straight one by one. Now I'm going to start off with the body and then move on to the neck and the fretboard after that. So let's hide the neck, and the very first thing that we do is actually the top here is not on there yet, and we want to just kind of prepare the stock body with all the internal things that will later be covered by the top, as well as with the arm bevel. I like to do a kind of bent top here that follows the arm bevel nicely, and this just means that I don't get an ugly line here and the beautiful top is seen everywhere. So here, this is my first setup. I have defined the stock here as a separate component with the body, and this just means that I get exactly what I need, and I can also have like the locating holes, for example, defined in the stock, and it's just a lot easier to manage than using like a fixed size box stock in here. I'm starting off by just facing the stock to thickness. Sometimes I do that separately before already. In this case, my stock was still a bit too thick, so I'm using a big 2-inch flattening bit here, so roughly 50 millimeters. This is really nice at getting like a nice even flat surface, and it's pretty quick. Now you do want to make sure that your spindle is nicely trammed, otherwise you will get some step over lines, but here this works great for me, and this is definitely an operation that kicks up a lot of dust if you are not using dust extraction. If we look in here, the spindle speed is of course slowed down quite a bit here. This is a huge bit. Now even at 12,000 RPM, the surface speed is a lot faster than I usually try to aim for in wood. However, this bit claims to work up to 15,000 RPM, and I haven't had any scorching issues running it at this speed. But this is definitely something I want to keep in mind. And then the feed rate I have at 5,000 millimeters a minute here. I'm sorry if you work in inches per minute, but doing every single conversion here would just take forever. So well, if you want to follow it along, it's probably easiest if you open up a millimeter to inch conversion in a separate tab. Then for the actual bevel here, I'm using a parallel strategy with a 12 millimeter ball and mill, and this is just the easiest way that I've found to just nicely step down. I'm doing very small step overs, so I don't have to rough anything out before, and it's a very even engagement as it just continuously takes more material. Now the main trick here is getting it to extend past the body shape here, as I haven't glued on the top and I want to have a bit extra that just kind of extends nicely so that I can glue on the top, have a bit of overlap where it still glues on nicely and it follows the curves. Now to do that, I created a separate surface body. This is, there's a couple of ways that you can do this here. The way I get this curve in the first place is I have a sketch here that's kind of perpendicular that I then extrude out to make the cut for the top. And I use the same sketch to create just a surface body, and then use an outline sketch from the top to cut it to the shape. And it just has a bit of an offset. Then inside of the parallel here in the geometry, I'm using the face contours of this separate surface, and I'm also using here the model tab, as this body here is not one of the models of the setup. I'm including it here as the model, and this will make sure that the tool doesn't drop down off the edge. For the step over here, I'm using 0.75 millimeters. This of course does leave some step over lines, but I can just sand those off very quickly, and this also makes sure that when I'm kind of stepping down quite deeply here in the end, there's still not too much load on the tool at all. Then for the RPM and speed, I generally want to aim for around the 550 to 650 meters a minute for surface speed. And this just basically dictates the spindle speed here based on your tool diameter. That's how I arrived at this speed, and that also means that basically the smaller the tool, the faster your spindle speed will be. Then for the cutting rate here, for wood, something in the 0.1 to 0.2 feet per tooth range is usually a safe bet. stay maybe on the lower side if your machine is not as rigid. And then this is how I arrive at the feed rate. After that, I'm switching to an 8mm end mill, just kind of doing a small little drilling operation here. This gives me a hole here that I will later use when I flip it over as well, but mainly for the next operation after I've glued on the top, this will be my 0 point, and I can simply probe that in, and this is the easiest way to get a precise reference. Now, it doesn't matter exactly that I'm on like down to the micron here. If I'm within like a millimeter or so, this is perfectly fine, as everything here is still oversized. I'm cutting nothing down to dimension. And even once I'm doing the internal routing here, if these routes are slightly off by like a half a millimeter or something, that is still perfectly fine, and that like you won't be able to tell. Now, this outline is not following it directly, but it's just gonna mainly here as like a visual guide of where I want to glue on the top. This way I can ensure that when I glue on the top, that if I am covering this everywhere, then I know that I won't like have a piece missing somewhere. And there's like, I think like a 5mm like stock to leave here on the radial, and this is just a guide that helps me lining up the top, but completely like optional. Then after having machined all of this, take it off of the machine, do some light cleanup. I use the bandsaw to cut away the excess material where I will attach the bent top. And to bend the top, I'm using just some heat and steam. This I'm doing with like a acoustic guitar side bending iron, but there's all kinds of different ways you can do it. Depending on the wood, like in this case, the poplar was so soft, I could have probably just gotten away with either just using some water to soften it, then clamping it in place, or even just forcing it in the vacuum back. But there's a chance of cracking, so I prefer to do it with water and heat. But if you're doing something like maple, of course, then it will require quite a bit. My tops are 5mm thick, which I find I can bend even maple still fine at 5mm. Any thicker than that, and I'm going to have a problem having it follow the curve. But I think 5mm is a nice thickness anyhow. And to glue it on, I'm using a vacuum bagging system here. I used to use a clamping caul, and that also worked. It's just a lot more convenient and faster with the vacuum bag, as I don't have to set up a caul and put on 20 different clamps. But if you don't have a vacuum pump, then clamping caul will work perfectly fine as well. Then after that glue has sufficiently dried, I can move on and cut the rest of the body. So here, starting off on the top, I'm cutting the remaining, locating slots, and if locating holes. I usually try to make sure that, well, this one down here is of course not covered. And by the way I'm making sure that this is still square to the machine, since I'm only taking one location here, is I just use one of these edges as a reference, and in case I cut that edge off or something, I align it manually using the center seam if I have like a two-piece body or something like that. Then I move on to cutting some of the cavities. Let's have a look at like just one of these adaptive operations, as they're essentially mostly the same everywhere. I'm using 8mm 2-flute end mill here. I might switch to a 3-flute at some point. I just haven't gotten around to changing it out yet, but I got one. This will just allow me to get out even more, but usually these adaptive are quite fast anyhow, and are not the limiting factor of how long the operations take. So that's why I also haven't gotten around to it. Now for the feeds and speeds for my 8mm mill, I have kind of two different recipes. One is for adaptive, where I'm just taking a side load and it's not like fully encased in the slot. Here I'm going a bit faster, 20,000 RPM and 5,500 millimeters a minute. And then if I'm doing slotting operation, I just slow everything down a little bit, and this just results in less load on the tool. It doesn't scream quite as badly. Since I need quite a bit of stick out on this tool to be able to clear all the way down, I can get some chatter and some screaming if I do slotting. That's why this is a bit slower. Then I'm just doing multiple depths. Usually I like to do around 10mm step downs. That works quite well. And a stock to leave between like 0.3 and 0.5 is what I usually like to do. Here I do a bit more on the higher side, 0.5, as later I'm going to come around, clean up the edge, and there I'm going to use a downcut end mill. This tool here is an upcut end mill, and it can result in a little bit of tear out. So if I have a bit more here, there's more meat to the left to kind of remove the tear out. The 3-flute end mill that I might be switching to is kind of a roughing with straight flutes and some chip breakers. I don't want to use a downcut end mill for these kind of bulk material removal, as it just packs down the chips a lot and kind of gets packed up more. I like to just have all the chips fly out easily and get removed. So straight flute might be a good compromise to minimize tear out while still getting all the chips out. Then, before I can continue with the other pockets, I'm actually cutting the outline. I'm not cutting all the way through yet. That will be once I flip it out over. So here I have a bit of a stock to leave. And what I'm also doing is I'm taking here a roughing pass. And this is not to kind of get a nicer finish, but this is just to widen the slot and allow for all of the chips to come out. Now, if you cut a slot that is very deep like this, the wood chips tend to not want to fly out. Now this was mainly relevant when I was still using a 6mm end mill on my Killer Bee, as I wanted to be able to get everything done with one end mill and not have 6 and an 8mm. So there the slot was even narrower, so having these roughing passes was absolutely necessary. Here with the 8mm end mill, it might not be strictly necessary anymore to have those, but this also gives me a bit more of a gap later when I come around to do some of the roundovers with the ball end mill. So I'm doing a 3mm step over here for the roughing passes and going down 2 step downs of 9mm each. Then this gives me enough access here as well that I can do the adaptive operation here, and I can just come in from the outside. I can just rapid plunge here and cut away the neck pocket here. Then I do same adaptive operation here. Now it's a 3D adaptive here that is just constrained to this area and set to only go down as far as it needs to clear everything from this side. And then I will go through all the way from the other side. This is all still with the 8mm tool, and then I'm switching to my 6mm downcut tool to do all of the finishing. This can also get into all the corners. All of my corners here I have designed with a 3mm radius, and this means that I can get in there. Now, if I needed tighter radii, I could of course use a smaller tool, but for basically anything I do here, 3mm is perfectly fine. So that just makes it easier. Then I also cut the holes here for the potentiometers, finish the pickups, the neck joint. Then I switched to a 2mm tool to cut the slot for the blade switch, as well as the holes here. I stopped doing the chamfers here on the machine, as it is easier to just do those by hand with a nice tear-out-free kind of countersinking bit. Then final things left to do are kind of the 3D stuff, the surfacing. So starting off with these bevels here on the horns. Now I'm using a 12mm ball end mill here, the same one that we used before to cut the arm bevel. And once again, parallel strategy, and I'm also not kind of pre-roughing this here. I used to rough all of my finishing strategies with ball end mills on the Killer Bee, and if you have a slightly less rigid machine, that might be a good idea to come in here with a 3D adaptive first to get the bulk of the material away and only finish with the ball end mill. But I find with a parallel toolpath, these are very predictable, and you can have a small step over and you're not actually taking a lot of load, and it kind of is a slow and gradual ramp up and ramp down. So this works out quite well for me, and I get a pretty good finish right off the bat. Then to do all the roundovers around, I'm using a scallop toolpath. I'm also using that to kind of do the recesses here for the knobs, and that just saves me a lot of time later for sanding. Now, I will refine these curves and sand them into a perfect shape, but it's just kind of gets the job started. Flipping over to the bottom side, I am now using all of these holes that I drilled previously to align it onto my CNC. I have a 50mm grid set up with 8mm holes on my CNC, so I don't have to actually drill any new holes here. I made sure that these ones are also on a 50mm grid. That means I can just use dowel pins, probe the hole that aligns with the one here beforehand, and then flip it over and align it with these pins. And that gets me to a repeatability of like 0.1, 0.2mm fairly easily. If I needed something more precise, I could build proper fixtures, but since I left a bit of stock to leave here on the contour and everything else, like woodworking here, I'm gonna sand everything later, so like 0.1, 0.2mm precision is more than enough for me. On the other side, it's more of basically the same, starting off cutting out the bulk of the material with some adaptive roughing strategies. And same thing for the battery and the tram cavity. Then doing some of the finishing. And then I cut the outline now from the other side also to roughly the middle point. And this now frees the remaining stock around. So, by the way, the way I'm holding on to this after I flipped it over is kind of the same as always. I'm just using masking tape and super glue. So I apply the tape to the piece, make sure to burnish it down really well. If you just lay down there and kind of lightly press on it, it doesn't hold nearly as well. You want to push on it either with a tape roll or with a separate roller and really push it on there, and then it actually sticks really well. You also have to, of course, make sure that it is flat, but we surfaced this surface here beforehand. If you just get a body blank in, they might have a slight twist to it, and then this tape thing is not going to work really well, as it might not lay perfectly flat on your CNC bed. Now, when I flip it over, there's a lot less surface area that will be contacting it, especially after I kind of remove the outsides. So I usually get like a nice tape strip in here around this area, and one in here, and sometimes in the middle. I found this works well enough. Some people like to leave tabs, but for me, I haven't really had any issues of it popping up, except one time, but then I did not flatten the top and, well, paid the price for it. But this way now, this is freed, but still both the center and the stuff around is still attached to the CNC bed and is not kind of flying off. Now, I do sometimes kind of pick away the outer edges, just so that they're out of the way, but, well, if you kept your fingers out of the CNC while it was running, then you wouldn't do that. Then after I do the outline, also the same roughing strategy, I go around again in kind of some coarser step downs and do the finishing passes. This now goes basically all the way down. I leave like a couple millimeters from the bottom since I have this fillet here anyhow. This just means that I don't have to cut into my spoil board. Then finishing up some other housekeeping items. The little recesses for the covers here, drilling the holes for them, and then doing here the bigger roundovers. Now here I'm again using a scallop toolpath, and with scallop you want to kind of do a roughing beforehand if there is more material that you want to remove, because it kind of goes all over the place. It starts from the outside and just kind of top and bottom and wherever. So you might all of a sudden take a lot more material in one pass than you intended to. This is kind of just on the edge of what I want to do. Otherwise, I would do a 3D adaptive before. I used to use the scallop for all of the different operations here, also for like the belly cut and everything. But I found that it kind of, these corners here where it changes directions, if that is kind of a concave surface that it is on, it can leave some little dimples here from changing directions that are kind of hard to sand out. So I'm just doing this scallop here on stuff that is kind of all over the place, as it is the simplest one to just constrain it, just select what I want and it does its magic. Then for the nicer surfaces here, I'm using once again a parallel toolpath. This leaves a much more consistent finish that is easier to sand out. Now you can also see that these kind of finishing strategies in terms of time make up the majority. Like half of the time cutting here is just these kind of surfacing strategies. So choosing the right step over
kind of doing the trade-off of how long it takes on the CNC versus how much sanding it is can save you some time. I do fairly fine step overs here, especially considering it's a 12mm tool. But then here for the heel, which I carve more by hand anyhow, I do a significantly coarser step over just so it goes faster, and I will sand all of that by hand anyhow. And that's basically it for the body. Now I have the body completely freed. I take it off the machine, admire it, and there's of course still a lot of sanding left to do, final shaping of everything, but that is the matter for a different video. Then moving on to the neck. I'm already starting off here with a kind of prepared neck plank that I already made ahead of time. It is for me 18mm thick, and then just kind of the width and length is just so that everything fits in here. So here I glued it up from the different materials and then used my drum sander to get it to the perfect thickness. Then here on the top side, the main things I have to do is kind of a truss rod slot in here. For this here, I'm using a 6mm ball end mill, and the reason why I'm using a ball end mill and not a kind of flat end mill here is it just leaves a nice radius here on the bottom inside of the slot, and most truss rods, at least the ones I'm using, are round, so this just leaves more material there that otherwise just makes it a lot thinner. My necks are very thin, and there is not a whole lot of material left, so if I can keep a little bit more material here in the corners and strengthen the neck up more, that is a good thing in my book. That's why I'm using a ball end mill to kind of cut that out. Now, here for the bullet, it steps over more and it leaves a little bit of a ridge here on the bottom. So I'm coming in, cleaning that up with the flat end mill before I'm using the 6mm flat end mill as well to kind of bore out these locating holes, which I then later use to flip it over, as well as the carbon fiber reinforcement channels. I like to use 6x6mm carbon fiber rods. I found that they work quite well, and they are very readily available from kind of carbon fiber suppliers instead of luthier suppliers, which means that for a meter I pay $10, and a meter is enough for one neck instead of the like $20 to $40 you pay for the same thing from a luthier supplier. Then after this quick top operation, I'm using these two holes again to flip it over as you have seen before. Once again, using masking tape and super glue to hold it in place. And then on the bottom, starting off with the outline, this kind of cuts everything free and defines the outline. Now, depending on what material I'm using here, here I'm use the 8mm end mill, since I have like walnut here on the outside, which is not very bad for tear out and chipping. But if I'm using Wenge, for example, I like to use the downcut end mill instead. And just in my machine, I have a 6mm downcut setup and an 8mm upcut. So if I want to have the downcut, I just would use the 6mm tool. But it doesn't really matter here what the diameter of the tool is. Then for the neck profile, here I'm not going directly to the finishing pass, but I'm doing a roughing pass first. Maybe that's not necessary, I just have it in here for nostalgia reasons, I guess, but like once again, the time it takes to rough compared to the finishing is so little anyhow, but maybe in the future I will not do these roughing passes anymore. But if your machine is not super rigid, then it's definitely a good idea to do the roughing first. This just means that the finishing tool doesn't have as much to remove. Then here I'm finishing with an 8mm ball end mill. The reason why I'm not using 12mm is just in order to get all the way to kind of the edge here, the tool actually dips down below the neckline, and this is just kind of necessary to get this shape, and this means it kind of dips into my spoil board. That's okay. If it was bothering me, I could elevate up the neck, but this is why I don't want to use the 12mm end mill, although it would leave fewer step over lines, as that would just have to go down even deeper. Not sure if I've actually showed you one of these finishing strategies before on the inside. So here I'm using 24,000 RPM with the 8mm tool and cutting quite fast at 5,500 millimeters a minute. It still takes 9 minutes to surface this, but well, that's what I get for using a 0.5mm step over. Now you can see that I have already finished the kind of neck before I glued on the fretboard. Now there's kind of two schools of thought, and the way I like to do it is do the neck and the fretboard separately and then glue them afterwards, completely finished together. This makes it much easier to hold, as I now here have just a flat surface that I can easily put down to the spoil board and finish everything. And same for the fretboard. If I glued the fretboard on first, then either I cut the fretboard radius as well first, and then when I flip it over here, I now have a round bottom that needs some sort of jig to hold it in, or I leave the fretboard flat, flip it over, but then when I cut the fretboard on top, then I no longer have a flat bottom here to clamp down. All of this can be solved with jigs and kind of special tooling, but for me it is just easier to do it the other way. Now, the advantage of gluing on the fretboard first, and it would just be that you make sure that it is already perfectly straight, and then after you have cut it, it will not move again. This can just kind of save you some time flattening it later and simplify it in that regard. Also, getting the clamping pressure perfectly even on this surface can be a bit hard without a vacuum. Now that I have the vacuum, I haven't had any issues anymore about the edges lifting up, but otherwise, like if you just put clamps here in the middle, here on the edges, there's not a lot of force holding it against the fretboard when you're doing the glue up, and you can kind of get a bit of gappage here on the side, which is of course not what you want either. This is much easier if you still have a rectangle that you're gluing together, as the clamping pressure is spread out much more evenly. Now that we have a neck, we need a fretboard to put on it, and usually the fretboard here and the kind of headstock veneer is two separate pieces for me, but since I'm using a very small headstock here with a block headpiece, I decided to keep it all in one piece. The material here is Ridgelite that I'm using, which is very nice to work with, especially for these thin features, as there's no kind of wood grain where it likes to split. Now, because it is Ridgelite and not wood which can chip out, I am using my 8mm tool here to do the outline. Otherwise, I would definitely use the down cut and mill to make sure that I don't get any tear out. The next couple of preparations here are also unique to this guitar, and just doing a surfacing, I'm surfacing the headstock veneer here by using a kind of just 2D contour, which is this edge here that I'm following, and then I'm just doing a bunch of step overs. This was the easiest way without creating a special sketch to constrain it and create a facing path here that does not go over at all, cutting this away. Then I come in with a 2mm end mill to cut out this inner piece. Since it's glued down with masking tape, I don't have to worry about this piece flying off anywhere. Then I'm using the same 2mm top tool to cut my nut slot. My thickness I like to do for my nuts is 3.5mm, so that works quite well with the 2mm tool. I then also use this same 2mm tool to get started on the inlay. The way I'm doing the inlay for this fretboard here is I'm cutting the pockets and then pouring in some epoxy. This means I just need to worry about cutting the pockets. I do not need to cut the pieces that actually fit into those pockets. It's just kind of basically a cheating way of doing inlay, as you're not actually inlaying it, you're more pouring it, but I digress. I also pre-surfaced the fretboard to just slightly above my final thickness. The final thickness will be 6mm at the thickest point, so the blank I prepared is around 6.2mm. That leaves me enough material that when I radius it, I can cut away material everywhere, but also means I don't have to cut the inlay any deeper than absolutely necessary. With the 2mm tool, I can still go down full depth. The depth for the inlay here is 2mm at the thickest point. And but then later, when we move to the smaller tools, I need multiple step downs. So the deeper I have to cut, the longer it will take. So the bulk material is removed with the 2mm tool. Then I move down to a 0.6mm roughly, or 0.58mm tool here. This is also what I use to cut the fret slots. And then here for the circles, I'm just using a bore toolpath. The feeds and speeds here are 30,000 RPM for me because I can. Same for the 2mm tool, by the way. just all the spindle speed already, like the surface speed is like teeny tiny. So I could easily, like, if I want a surface speed of 550 meters a minute, I could use 3,000. I could use 300,000 RPM, and surface speed still wouldn't be too much. So use all the RPM you can reliably use with your spindle. Then the cutting feed rate here is 2,000 millimeters a minute, but actually I don't really even look at that too much. What I look for, especially for these kind of very small and fragile tools, is the feet per tooth. And a kind of rule of thumb that you can use is you want to use like 3 to 5% of the tool diameter as your feet per tooth number. So if we take our 0.6 millimeter end mill and multiply it by 0.03, we want minimum 0.018 millimeters of feet per tooth. So here I'm slightly above, so I'm probably at around 4% feet per tooth. Now the tool I'm using here is from Precise Bits, and they have sent over a couple of bits for me to try. Now, they didn't tell me to use them in a video or anything, just wanted my feedback, but I'm very happy with them. And they also have a lot of resources on the website, so we'll have it linked down below. They have all kinds of calculators and a bunch of knowledge articles that tell you how to cut different things for loose theory and some other disciplines as well. They go into this whole kind of 3% thing a lot more, and if you are curious about it, you can go check it out. I had a great talk with Ron from their support staff, and he taught me a bunch of stuff for using these micro tools. And so I'm very grateful to them, and I can now relay this knowledge further to you. Now, before I was going quite a bit slower than that, and especially what I did less before was the step down. Now, if you're just cutting woods, let's maybe exclude very hard ebonies like African ebony from that. You can always step down 1 times your tool diameter. So here I'm actually put slightly less for the pitch. And I also like to use, instead of ramp angle, I like to use pitch. So here I could actually go down 0.6 millimeters, which before, for these tools, I was using just like a 0.2 millimeter step down, and going up to 0.5 or 0.6 just makes it a lot faster. And actually, the tools are holding up. Now, of course, you also want to make sure with these tiny tools that you are using a collet that doesn't have a lot of runout. So if you're just using the cheap Chinese ER collets that came in a set of 20 for $20, you are going to have a terrible time. You want to get some really high precision ER collets, as usually the spindle is a lot more precise than the cheap collets. Even a cheap spindle can usually get you by if you put in a nice collet. Then I'm using the same 0.6 millimeter end mill with an adaptive strategy to clear away the material I was not able to access before with the 2 millimeter tool. Now in here I'm just using the rest machining functionality. So here you can take rest machining, and I have it actually set slightly larger than the tool diameter, because if you go into passes, by default you have a minimum cutting radius, and that just means that it doesn't go all the way into the corners. But then if you just use the tool diameter, and before on the 2 millimeter end mill, for example, I might have had a minimum cutting radius of 0.1 millimeters. That means that there is actually more material left than just the 2 millimeter tool could theoretically access. This is why I'm setting the tool diameter slightly higher here. And then once again here, the step down, I have 0.6 millimeters. And for the heights, you want to make sure that you are using the stock the stock top as your top height, and not the model top, as we have not removed the kind of radiusing from it. So you would actually take it too deep of a step down in the first go around otherwise. And while my logo looks fine like this, this inlay here still has a lot to be desired. So I actually am going back in with a 0.4 millimeter tool here. Now I might have said 0.3 in the intro, but the benefit of the 0.4 millimeter tool is that it is available with a longer reach. And ideally, you want to design your inlay that you are not going to use a smaller tool than 0.4 millimeters. And generally, an inlay that has finer details than a 0.4 millimeter tool can reach is also not going to look that great because it will just be too fine and get lost. Now here I am using once again an adaptive strategy with rest machining. However, it turned out not to be the best strategy for this specific inlay design. Now, I don't usually work with line drawings like this, so that's why I didn't even consider that. But the issue here is that these lines, instead of kind of cutting them as lines with the adaptive, are cut with teeny tiny little circles. And well, my machine has decent accelerations, but still, on these teeny tiny little circles, it will never reach the 1500 millimeters a minute of cutting feed rate. We will be more like in the 200 millimeters a minute cutting feed rate. Which then means instead of having the proper 3% tool load, I might have only 0.5% or even less. And this then results in you not actually cutting chips, but just making dust. And the dust doesn't really clear out properly and just kind of clogs up these slots. And also the tool can heat up more because it is rubbing more. This actually resulted in the tool breaking here on the very last step down. Now it was still fine for the inlay. It is deeper than it absolutely needed to be, so it broke just in time. But next time for this kind of a shape, I would use the adaptive with the 0.6 still to kind of get into all the corners. But then here for just these lines here, I would use a 2D contour and go around, and that would not only be safer on the tool, but it would also be a lot faster. Doing these kind of tiny swirls here took 16 minutes calculated, but I think the real time was even longer than that. Then after all of this is cut, now before I do any of the radiusing, I'm going to go in and pour epoxy into all of this. For this one, I'm using epoxy resin with a bit of a glow-in-the-dark powder mixed in, which should give a nice glow-in-the-dark effect. Now, especially for all of these small paths here, you want to really make sure that you don't have any air bubbles trapped in there. So I use like a tiny little toothpick thing to kind of get in there and make sure all the air bubbles are out. I'm also using like a heat gun to not just pop the bubbles on the top, but also kind of warm up the epoxy slightly so it gets a bit thinner and runs down into all of the cracks. The last thing you want to have is like a nice inlay that has air bubbles on the bottom that after you surface it off, you now have a big hole that you need to fill. Another trick, if while the epoxy is drying, you want to keep continuing to use your CNC, is that usually I'm just using the G54 work coordinate offset. And if you don't know what that is, you're probably also using G54. But here, for the fretboard, I actually like to go into the post-process section of the setup, and for the work coordinate system offset, having nothing set or 1 puts it at G54, and I set a 2 here, which puts it at G55. And what that essentially means, it just kind of saves an additional location as the 0 point. Now, if you are probing in the 0 point, you need to make sure that you are already in G55. Otherwise, if you probe in the 0 for G54, then run your program, the 0 point will be in the wrong place. Don't ask me how I know that. But the whole point to this is that this is now saved at my G55 location. And while the epoxy is drying, I can still continue using my CNC as normal at G54, and the location here will continue to be saved at G55. And then when the epoxy is dry, I can just run my other program at G55 as well, and it still has the location. And I don't have to try and probe anything in again. You can also use this if you're doing multiple fretboards or other things at the same time. You can just continue going up. Depends on your controller how many you have available, but most controllers will have a couple working coordinate systems that you can use. So you can use 355, 56, 57, and so on. Then after the epoxy has fully dried, and while it is kind of is set after like 24 hours or something, I like to keep it for a bit longer, as the one I'm using at least tends to shrink slightly afterwards, after it has already cured. So by leaving it for about a week, I make sure that the shrinkage has happened before I surface it flat. Otherwise, I've had it before where I cut it nice and flat, but then later the kind of inlay sunk in a little bit because the epoxy continued to shrink. Then for radiusing here, this is another area where I made some changes to what I used to do. I used to use a big, like 1-inch ball end mill. This worked quite well, and like it has a nice big radius so that the step over lines are quite small. However, I found a better option in my opinion, and that is also by Precise Bits. They make a end mill specifically designed for flattening fretboards. Now, originally they designed this for the Plek machines, but you can use it on any CNC machine that you like. Now, what this tool is a 3mm or 1/4 inch, if you like, bullnose end mill. So it has a flat bottom, but it also still has a corner round. Now, it also has some other fancy geometry that is optimized for this job, but that is beyond what I understand. But what this means is that if you are cutting just a very shallow radius, you can use the flat on the bottom to get basically no step over lines. But still, you are not getting kind of sharp transition points where you are stepping down because you do have this bit of a radius. This means that doing the recommended step over for this tool of 0.5 millimeters, I get basically no cuspide. The result here, you can ever so slightly see and feel the ridges, especially on ridge light, but if you're using wood, like ebony, or especially on something like Wenge, which has coarser grain, the fretboard is basically perfectly smooth already, and you will require very little sanding. Now, because this is a 3mm tool, I am running still at 30,000 RPM spindle speed, and you can actually go really fast cutting speed. It's a 3-flute tool, and running at 30,000 RPM, here my feet per tooth is only 0.09 millimeter. I could go faster, but I'm already at 8,000 millimeters a minute of speed, which is very fast. Now, there's a good chance that your CNC might not want to cut this fast, so you will just have to go as fast as you can or drop down the spindle speed a bit. But this means that although I'm taking very small step overs, this still completes relatively fast. Another quick trick here, because I want to be able to kind of get nice corners, I want to cut a little bit further, but following the same radius. So once again, here in the geometry tab, I'm using just the outline as my kind of bounding box, but then I'm using the tool outside of like the bounding as my limit. This would normally cause the tool to kind of drop down off the edge. But what I'm doing here is using the model. And here I once again created a surface body that follows exactly the radius. And this means that it will just keep following that. And I selected this body here. And that is just a nice workaround to get it to go all the way off of your fretboard. With it nicely radiused, we then move on to cutting the fret slots. And once again, Precise Bits has come through for me here, not just by supplying me with some really nice bits, but especially with supplying me with more knowledge of how to do it better. I used to use a 0.6 millimeter end mill and just do tiny 0.2 millimeter step downs. I did like a dozen of them, and it took about half an hour, maybe 20 minutes after I bumped up the speed a little bit to cut all of them. And then afterwards I would have to still go in and nicely chamfer all of the edges before I install the frets. Now, instead of that, I am starting off with a 60-degree V-tip tool. So we have a V-tip tool, and it is a tool more designed specifically for kind of scribing like that. And the main difference here is that the little flat spot here at the top tip is quite large compared to like an engraving tool. Like if this tip here is too small, then your feet per tooth might actually be bigger than the actual tip diameter, which basically means that you cannot cut that fast. What will happen is that you either break off the tip or you just drag it through or something like that. So having a slightly wider tip diameter here is really nice if you are just kind of slotting through. So this tool I have set up here, you can see that I actually did not model the fret slots in here. Instead, I have a sketch. Instead, I have a sketch here where I took the fret slot locations and then I projected them onto this surface. And then that gives me these fret slots and kind of just a line that I can then follow. Then I'm using the trace toolpath in here, selected all of these lines as open chains and set a start extension length of -2 millimeters, same for end. This will just mean that you have a little bit of fake binding that will hide your fret hanging. And you could also manually make sure that the sketch doesn't go as far, but it is a lot easier to do this in here if you project the fret locations. Then for the passes in here, for the trace toolpath, it will by default just trace out exactly that line. So you need to set an axial offset here down. Now, how far down you need to go, you kind of need to use some math, or you can make a sketch in a different Fusion file to figure out. What I want is a 0.6 millimeter fret slot with a like 0.125 millimeter chamfer on either side. This results then in an axial offset of 0.72 millimeters that I need here. If you're using a different angle for your tool or have different widths, that might be slightly different, so you want to make sure to compute that again for yourself. Now, after this slotting tool has gone through, all of the fret slots are pre-scored. And what this does is it doesn't just eliminate the step of having to chamfer them afterwards. What it also does is, this doesn't really apply to Ridgelight as much, but to woods that are more prone to chip out, is by having a chamfer already, the edge is a lot stronger, and then cutting the fret slots afterwards will not give you any tear out. So I recently did a fretboard in black palm, which is just notoriously bad for tear out, and there I definitely could have used this trick. I didn't know about it yet, but I had massive tear out from cutting the fret slots, which I then later had to fix. Then for the actual fret slots, we already cut partially down, so I only require 3 more step downs of 0.6 millimeter step down, since we're using a 0.6 millimeter tool, and then I'm going down to a final depth of minus 2.75 millimeters. This is deeper than I need to go, but I will later still flatten this fretboard, and I just want to make sure that I'm definitely deep enough. I'd rather go a bit deeper than I need to than have a fret slot that is not deep enough in the end. So here I'm still using 2000 millimeters a minute of feed rate at 30,000 RPM, and that results in the actual cutting of the fret slots being only roughly 3 minutes, plus another minute for the chamfering. So 4 minutes to cut the fret slots versus 20 minutes or more that I was using before. That is an incredible improvement in just time it takes to cut this stuff. This covers all of the major components here of the guitar. Now there is still a couple other like little covers and things and whatnot that I like to do sometimes, but this video already is very long and I'm definitely tired from talking, so I'm gonna cut it off here. Now there are a million different ways that you can skin the cat of cutting something on the CNC. If you ask 10 luthiers who use the CNC how they do the strategies, you will definitely get 10 different answers of doing it in different orders, different philosophies, different ways of holding it down, different ways of locating, all of that. But I hope you got some ideas of what you might be able to try for yourself. Of course, if you have any more tips, you can leave them down in the comments, and that way other people can read them and get even more ideas and knowledge. I'm always evolving my own process, and if you ask me again in a year what I'm doing, it is very possible that I will have different strategies that I'm using than what I showed you here today. And with that, here we are, all of the components are here. Now the next steps are going to be gluing up the fretboard to the neck. I'm going to use my vacuum system for that. This allows me to have even pressure on it and make sure that everything's nice and tight. And then I'm going to sand everything, glue in the neck, build the rest of the guitar and all of that good stuff. Now, if you want to see more how this guitar turns out, make sure to follow me on Instagram, link down below, or you can also check back on my website in a little while. Once the build is done, I will post full pictures there, just no live updates. Before you ask, no, sadly this guitar is not available anymore, but I do still have a couple of in-stock guitars, so you can also check those out, linked down below on my website. So with that, thank you guys for watching. Another big thank you to Spinergy for this spindle. And I'll see you guys next time.